Welcome to EPG Pathshala in Computer Science. This is a series of lectures in computer networks. So, we will be looking at some wireless technologies. As part of that, in today's module, we will be looking at cellular networks. So, we will look at the basics of cellular networks and we'll start from the second generation of the cellular network. So, we will look at the 2G basics, then we will also look at the architecture of 2G cellular network and we will look at how mobility is handled in 2G networks. Okay, so let us start with the principle of a cellular network. So, it is basically the underlying technology for all our mobile phones, personal communication systems, wireless networking and so on. And it has been basically developed for mobile radio and telephone. Initially, it was meant to replace these high power transmitter receiver systems that we had. Typically, it supports about 25 channels over 80 kilometers. And the idea is to use low power, shorter range and more transmitters. So, the reason we are talking about high power versus low power transmitters is that initially when they started off with wireless networking, you had one single huge transmitter for an entire area like a city and all receivers were connecting to that one single transmitter in order to transmit data to each other. So, obviously, this was not a very viable solution because you needed a lot of power to be able to communicate with these with that central device. So, which is why the idea of dividing an entire region into small cells and using multiple antenna in each of these things was proposed, and that is how the cellular technology was born. Okay. So, the basic idea that we have in cellular network is that we have multiple low power transmitters, typically 100 watts or less. So, the entire area is divided into what are called as cells. Each has its own antenna and each has its own range of frequencies on which it will operate. And each area is served by a base station. So, it has a transmitter, a receiver and a control unit. Adjacent cells, they work on different frequencies in order to avoid the crosstalk. So, obviously, two adjacent cells cannot use the same set of frequencies because that would end up in some kind of an interference. So, adjacent cells use different frequencies. So, this is the basic idea that is used. So, the overall cellular network structure would look like this. You have these cells, you can see that the area is divided into cells. There is a central base station. The different devices could talk to that base station using a wireless network, right? It is a cordless connection that you have. And these base stations are connected to a mobile telephone switching center, right, which is called the MTSC. There is some information that is maintained at these switching centers. So, which is called as the HLR and VLR. HLR stands for the home location register, VLR stands for visitor location register. So, the home location register keeps track of the different details about the subscribers who are subscribed to this particular MTSC. VLR keeps track of those nodes or those users who are visiting this particular location. So, remember that with the cellular network we support mobility and people can move from one area to another and also from one within the range of one MTSC or within the what do you say, within the control of one MTSC to another MTSC. So, when you have users moving from one MTSC to another MTSC, the details of those who are visiting that area is kept in the visitor location register. Okay. And then this MTSC will be connected to the public switch telephone network, the PSTN network, so which is now connected to the rest of the different other networks. So, it is only through the MTSC that you get connected to PSTN and you are able to make calls to other telephone networks. Okay. So, this is the basic structure. Okay. So, if you look at the cell geometry, the cellular geometries as such, you could have for instance a square pattern. You have the antenna right at the center, right, and you can have for instance adjacent cells which are all square in shape. So, what happens in this case is you can see that for the ones which are horizontally and vertically adjacent, the distance between two of them will be d, between the two centers will be d, whereas if you look at the diagonally adjacent ones, you can see that the distance will be 1.414 d, right. So, it will be more than what you have over here. So, you find that there is some kind of a, heterogeneity, right, in terms of how the distances are. So, in order to kind of avoid this and avoid certain problems that occur with respect to transmitting a different frequencies when you have this kind of a geometry, we go in for a hexagonal pattern. So, if you go in for a hexagonal pattern, you can see that each cell will have 6 neighbors and the distance to each of the neighbors, right, to the center of each of the neighbors, you can see will be a constant t. So, it becomes easier for us to handle the adjacency and handle various things, as we will see in with respect to cellular networks, right, when you have this kind of a geometry. So, the hexagonal pattern is what is chosen. So, now one of the very important aspects of cellular network is this idea of reusing the frequency. Okay. So, we said that there will be a set of frequencies that are there for each cell, and the same set of frequencies can be reused by another cell, provided that cell is not adjacent to the current cell, right. Because obviously if they are adjacent, you cannot reuse the same frequency because there will be interference. But if these frequencies are reused at a cell which is a little away from it, so that it will not interfere, the signal from one will not interfere with the other, you can reuse the frequencies. The advantage of doing this reuse will be that you will be able to increase the number of users that you can support overall, okay, and you are able to make better use of the available bandwidth that we have. Okay. So, with frequency reuse, the points to remember are this: the power of the base transceiver will be controlled. Now, why should this be controlled? It is controlled such that it will allow communication within the cell on the given frequency. You have to also make sure that the power is not very high, that it goes and interferes with some other transmission that is taking place on the same frequency, some other cell which is a little far away. Okay. So, you have to limit the escaping power to the adjacent cells. So, that is one thing. Okay. So, that is something that you gain by having the power of the base transceiver in a controlled manner. Okay. And of course, this allows us to reuse the frequencies in nearby cells. So, you can use the same frequency for multiple conversations. So, typically we have about 10 to 50 frequencies per cell, and for example, if you had n cells all using same number of frequencies as such, and k is the total number of frequencies which are used in the system. So, each cell, let us say, has k by n frequencies. Okay. Now, for instance, in AMPS, just the first generation cellular networks, you could have a value of k as 395, which means you had k different, total number of frequencies available is 395, and you had about n equal to 7, n cells having the same frequency. So, we will see how this these n cells, these 7 cells are actually chosen. So, totally you get about 57 frequencies per cell on average. Okay. So, this is the idea. Right. So, let us look at these different frequency reuse patterns that are available. So, we could have a very simple reuse pattern of 4. So, you can see, for instance, I take this cell here 1, right. So, 1, the adjacent cells here, you can see that adjacent cells cannot use the same frequency. So, you cannot have, if I say 1, 2, 3 and 4 are 4 different sets of frequencies, right. Then you will find that adjacent to 1, you will never find another one. You will either see a 2, a 3 or a 4, a 2, a 3 or a 4. Okay. Similarly, with respect to 2, you will see 1, 3, 4, 1, 3, 4. Okay. You will not see the same frequency anywhere adjacent to this. Okay. So, this is one kind of a reuse pattern where your n is equal to 4. Okay. Now, let us look at another reuse pattern where n is equal to 7 as in the example that we just alluded to last in the previous slide. So, here you will see that there are 7 different frequencies. So, 1, 2, 3, 4, 5, 6, 7, 7 sets of frequencies. Okay. And the first set, you can see if this is set 1, you will find that none of the adjacent cells have the value that is used by 1. So, it is either 2, 3, 4, 5, 6, 7. Okay. Same thing you can see for all. And where is the next cell which is using a frequency of 1, frequency set of same as 1, you can see that it is at least about 3 cells away. Okay. So, the reuse distance that we have, right. So, you can see that it is being the cell which is using the same set of frequencies a little further away. Here you will see that it is just about 2 cell distance, right, from here to here there is about a 2 cell distance. Okay. So, as we increase the reuse pattern, the n value, right, you will find that the distance that we have between 2 different cells using the same set of frequencies increases. So, which means that you have better separation of the frequency. So, it becomes easier to build the transmitters in these in each of these cells. Okay. So, this is one thing. So, you can see that if I use an even larger value of n, say let us say I use a value of n equal to 19, okay, you can see that the distance is even larger, right. So, for instance, the black cells are the ones which indicate which are using the same frequency. Okay. So, you can see that they are all further away by a much larger distance. Right. So, this is so you can choose different reuse patterns depending on the kind of what do you say, the traffic that you have and how much of frequencies are available and how you want to distribute them and so on. Okay. So, but this is the basic idea. Okay. So, now how do I increase the capacity? Now, we have said that so many channels are available right, and we are allocating certain number of frequencies to each cell. Okay. Is there some way in which I can increase the capacity if necessary? Okay. For instance, if there are more than, suppose we said we could at a time support only 50 calls in a particular cell. Suppose we had to support more than 50 calls, what do you do? Okay. One thing that you could do is, you could add new channels. Okay. So, for instance, normally not all channels are used to start with, so you could add new channels, but that may not be always feasible because the frequencies, the spectrum are getting used up quite a bit these days. Okay. So, it may not be always possible. Another option that we have is what is called as frequency borrowing, which means you could take some frequencies from adjacent cells. Okay. That is, if a particular cell is congested, that cell could borrow adjacent frequencies from adjacent cells if they are not being used by that particular other cell. Okay. Or in other words, you could assign frequencies dynamically. So, that is also another option that we have. Okay. So, another third option that we have is what is called as cell splitting. Okay. So, this is especially useful when you have a non-uniform distribution of topography and the traffic. So, for instance, in certain areas, for instance, even in a city, there are certain areas, for instance, downtown or a particular township, where you may find it highly congested. There are a lot of calls that are going on in that particular area. Whereas in certain outskirts, for instance, there may not be so many calls that are there. So, in which case, you will have a non-uniform distribution of traffic. So, you can try to see if you can use different sized cells in different areas. So, you can use smaller cells in areas where there is higher use. Okay. For instance, you could have something like this. Okay. So, your normal cell size is this, right, but in areas where you find that there is a higher frequency or higher traffic, you can see that you can divide it up into much smaller cells. So, you have a same region now divided into much smaller cells. Okay. So, the original cells is about, if it say 6.5 to 13 kilometers, okay, 1.5 kilometer limit in general. So, you can have the smaller cells at a 1.5 kilometer limit, right. And of course, you will have more number of base stations now, because each of these little cells now need to have a base station, and you would also have more frequent handoff. Handoff now is what happens when you move from the range of one base station to another base station. So, your call has to be kind of handed off from one base station to another base station. So, if you have smaller cells, obviously as you move there will be more number of handoffs that will have to be done. Okay. So, that is that's something that you will have to handle in the case of cell splitting, but it helps you to manage the traffic with the available set of frequencies. Now, another idea that is used for increasing capacity is what is referred to as cell sectoring. So, in cell sectoring, what we do is the cell is divided into wedge shaped sectors. So, that is, you have some kind of a directional antenna that is used. So, you do not have a 360-degree transmission, but you have transmission only in a particular angle. Okay. So, you have what are called as directional antennas. So, now each of these sectors, so as we call them, okay, they can have their own channel set, which is a subset of the cell's channels. So, that way you will be able to share the available frequencies even better. Okay. Another idea is to have what are called as microcells. Okay. So, for instance, you move antennas from top of hills and large buildings to tops of small buildings and sides of larger buildings. So, even for instance, lampposts can be used. So, you form smaller microcells. The idea is that you can reduce the power even still further, right. So, reduced power, and it can be good for areas like city streets, along roads and inside large buildings. So, you can have microcells and use these microcells to increase the capacity. See, these are different options that we have. Okay. So, in general, if you look at how these cellular networks have evolved from the first generation to the proposed fifth generation that is likely to happen, right. So, starting from 1980s, so you can see that these dotted lines, kind of these dotted areas, right, they indicate research and standardization. That is when there is a lot of work that is happening on some kind of research on that particular technology and standardization. So, once it is standardized, it actually gets commercialized and is used. So, you can see that the first generation was started off early in 1980s, but was kind of commercialized around 90s. Second generation, you can see up to 2000 it was still under research and standardization. 2000 it has been standardized. So, we have GSM, GPRS, EDGE are various standards that have been used in 2G. Then 3G spectrum auction kind of happened around this time when 2G was standardized. So, at that time you can see that the research for 3G has almost started, and around 2010 you can see that 3G has been even before that, right, it's been standardized, and 4G for instance has been standardized starting from 2012, 13 and so on. Okay, and already work on 5G has started. Okay, and the hope is that by 2020 we will be having 5G standards, and 5G will probably go on for another 10 years at least. So yeah, so the technologies that we have with 3G are WCDMA, HSPA, HSPA plus and so on. With 4G we have what is called as LTE, long term evolution, LTE advanced, okay, and 5G we are yet to see what kind of technologies are going to come. Okay. So if you look at all these different, whatever be the generation that we have, there are certain issues which are vital to cellular. So if you look at what these issues are, one of course is frequency allocation. So we've seen that normally the frequency allocation is done in a licensed manner. So there may be many providers. So you license out different frequencies to different providers. So this is something which is common across all generations, which is why you will see that there is an auction of the spectrum that takes place for each generation. Okay, it will be provided. So we do an auction and kind of give different frequency bands to different providers. Okay, so then another very important aspect is how we support multiple access, because many users are there in a given area, and we need to have wide area of coverage, and we need to do traffic management. All these things have to be done given that we have a multiple access technique. So what kind of multiple access techniques are suitable? Okay, that's another thing to look at. Third thing to look at is location management, especially when you have high mobility scenarios, as when you are traveling by car or train or whatever. Then how is it that you are able to support mobility, right? When you have multiple suppliers, how do I support mobility? So how is this handoff management, especially when you are roaming, right? So how do you handle location management or handoff management when you are roaming and so on? So these are some of the issues that come when you are looking at location management. The general principles we will see are kind of handled a little differently by different generations, but overall these are the issues that have to be handled by any cellular technology. Okay, so we will take a look at the 2G technology, and then we will see how other things handle these different issues. So if you look at the multiple access techniques, okay, there are a few commonly used techniques. So we have what is called as time division multiplexing, frequency division multiplexing, right? So in frequency division multiplexing, what do? The entire channel is divided into frequencies, and each frequency band, for instance, sub-band for instance, is given to a different session. So they use that frequency for the entire duration of time, right? So you can see if you have time and frequency here, for the entire duration of time, this frequency will be used by a particular user or a channel. Now in time division multiplexing, we have, you can see that time wise we divide, that is the entire set of frequencies is available or a particular frequency is available, and the time wise its use is divided. Okay, this is what is used in our 2G TDMA, time division multiple access, and 3G TDMA and so on. Okay, right. And then we have what is called as CDMA, which is code division multiple access. So in CDMA what we do is all sessions can use all the frequencies all the time, right? So which means all sessions are kind of, they share the frequency and the time domain that is available, but they use different codes. And because they use different codes, they are able to effectively share the channel without any interference. Okay? So you need to understand how that happens. It's very easy to understand frequency division and time division multiplexing. Code division multiplexing is a little trickier to understand. We'll take a look at all the three now. So if you look at time division multiplexing, very simple. So access to channel is in rounds. So you kind of divide the entire time duration that is there into multiple slots. Okay, and each slot is allocated to a particular station. So each station gets a fixed length slot, and length normally specified in terms of packet transmission time, okay, in each round. So you may have multiple such rounds that we have. Okay. So in this example, for instance, stations, let's say 1, 3 and 4 are transmitting, okay, 2, 5 and 6 are idle. So the unused slots, right, if 2 and 5 and 6 are not transmitting, those slots will go idle. So that's one of the disadvantages of TDMA that we have. Okay. Now in frequency division multiplexing, right, FDMA, multiple access, see what happens here, we have different frequency bands that are available. So there are multiple frequency bands which are sharing the same channel, right, same cable. So the channel spectrum as a whole is divided into frequency bands. Each station is assigned a fixed frequency band, and the unused transmission time in the frequency bands will go idle. Just as in TDM the unused slots go idle, here the unused frequency bands will go idle. For instance, here say 1, 3, 4 have a packet. Now the other 2, 5 and 6 do not have a packet, those lines will go idle. Those frequencies are unused. So other techniques that are commonly used, you will see are a combination of FDMA and TDMA. That is, you divide the spectrum into frequency channels and then divide each channel into time slots. So this is something which is commonly used. Okay. Another one that is used is CDMA, of course, code division multiple access, where you will have frequency slots and time slots. Okay. And in these frequency slots and time slots, the entire slots will be used up by the different channels using different codes. Okay. So let's look at this CDMA. Okay. So the basic idea here is that each user is given a unique code. Okay. So you can refer to it as some kind of a code set partitioning. Okay. So these codes are chosen in such a manner that they are orthogonal to one another. Okay. So which means all the users could share the same frequency, right? But since each of it has is unique code, which is called as a chipping sequence, which is okay, which is used, and that is used to encode data, you will be able to allow multiple users to coexist and transmit simultaneously with minimal interference. Okay. Now all this happens because the codes are chosen to be orthogonal to one another. So remember, if they are orthogonal, you can always separate them out easily. You can look at orthogonal as saying the two vectors. When we say they are orthogonal, we say x dot y is 0, right? So similarly, so that's the same idea that we use. So if you can represent the codes as vectors, and if you choose these vectors such that they are orthogonal to one another, you've got your codes which are orthogonal to one another. So by using such codes, we can now transmit data simultaneously. Okay. So the encoded signal is basically found like this. That is, you take the original data that you have and you multiply it with the chipping sequence. So that becomes your encoded signal. And your decoding signal is the inner product of the encoded signal and the chipping sequence. Now remember, inner product is what I just talked about. If I have two vectors, the dot product of the two vectors is what is called as the inner product. So you take the encoded signal and you do a dot product of that with the chipping sequence, you will get back your original data, right? So you can just see you're doing the opposite of this. So you get back your original data, right? So that's the idea. So we'll take an example to understand this. So let's say I have a sender, right, who is going to be sending some data in slot 0 and slot 1, let's say. Okay. So let's say he is sending a 1 in slot 0 and this is his chipping sequence. So to send a 1, he actually sends a pattern of, let me start from here, this is the first bit that's going out, let's say. So minus 1, minus 1, minus 1, 1, minus 1, 1, 1. So let's say this is the pattern he uses for sending out a 1. Okay. Now in slot 1, right, so let's say he is sending a value of 0, or let's say it's a minus 1 that he is sending. So minus 1 normally is used to indicate 0, 1 to indicate 1, for instance. So minus 1 you can see will be the exact inverse of this. So you had, for instance, will be the exact opposite of that, right? And you can see that the channel output that we have over here, you can see what is happening here. So when this pattern is sent over, a minus 1 and this is multiplied together, what you get over here you can see is you will have 1, 1, 1, minus 1, 1, minus 1, minus 1. You can see that what you have here is the inverted value of whatever we have here. Okay. So we can see that you have a slot 0 channel output showing that it has encoded a value of 1. Slot 1 channel output has encoded a value of minus 1, right. So that's the output of the channel. So that's what is happening in this encoding block that we have here. Now this is transmitted, okay, and it comes to the receiver. So at the receiver, let's look at what happens. Okay. At the receiver, I am getting this particular data has come in, right. So now at the receiver, the code that I have is this. I know that this is the code that I am looking for instance. So what I do a dot product of this code and this code. When I do a dot product of this and this, now since all of them are identical, I will get a value of 1, right. So I know that my slot 0 channel output is 1. And when I do a dot product of this value and this value, right, you have 1 here and a minus 1 here. So what is it you will get when you do a dot product of this? You will get a value of minus 1. So I know that the data that was transmitted here was a minus 1. Okay. So this is the idea that is used in encoding and decoding of CDMA data. So let's look at what happens when we have two users sending data simultaneously. Here we saw an example where only a single user was sending. Suppose two users are sending data simultaneously. Let's look at what will happen. So sender 1 has got this code, right. Sender 2 you can see has a different code, right. You can see that the 1 here, okay, and he is also transmitting a 1, he is also transmitting a 1. But you can see that the codes that are used by the two are different. So now what will happen is, when this will in slot 1, when he is transmitting a 1, his 1 will be multiplied by his code. Sender 2's 1 will be multiplied by sender 2's code, right, and that value is what will be added here. So when that is added, you can see that you will get in some slots you will get a value of minus 2, in some slots you will get a value of 2, and some slots you will get a value of 0, which means a 1 and a minus 1 kind of cancelled each other out. Okay. If you had a 1 in both slots, in one chip sequence, right, you will find that 1 plus 1 will give you 2, minus 1 and minus 1 will give you minus 2. 1 and minus 1 if you had, that will give you a 0. So this is the sum output of the both these data. So the channel basically sums together the transmissions by the sender 1 and the sender 2. Now this summed output is what will actually be transmitted. So when this is transmitted, so let's look at how a receiver 1 will be able to receive the data. So let's say receiver 1 wants to receive the data from sender 1. So what does he do? He will use the code of sender 1, okay, and do a same inner product with this some data that is received. So look at what will happen in that case. When he does that, you will see that you get the he will get in this slot. In slot 1 he gets a value of D0 equal to 1, and in slot 1 he gets a the D value as -1. Okay, so this is how he will be able to identify what was the data that was originally sent by the sender 1 in these slots. Same thing if he were to do with the receiver 2, or for instance if he were to AND it with sender 2, he will get the data that was sent by sender 2. Okay, so this is basically how the CDMA mechanism works. So now coming to the 2G network architecture that we have, so as we said earlier, so we will have multiple base stations, and these base stations are connected to what is called as a base station controller. So you will have one BSC controlling many base stations, and these base station controllers in turn are connected to a mobile switching center, okay, the MSC. Now the MSC is normally connected to a telephone network, the public telephone network, by means of what is called as a gateway MSC. Okay, so this is the overall structure that we normally have for transmitting voice. Okay. So as we said earlier, the base station is at the center of each cell. So it has antenna, controller and transceivers, and the controller in it handles the entire call process. So number of mobile units that are in use at a time can be any number. All that is to be handled by the controller. Okay. So the BS, as we said, is connected to the mobile telecommunication switching center, MTSC, and one MTSC can serve multiple BS. And the MTSC to BS link may be wired or it could be wireless. Okay. And the switching center, right, the mobile switching center, that is the one which is responsible for assigning voice channels, performing handoffs, monitoring calls, billing, all that is handled by the mobile switching center. Okay. So there are normally two channels which are used, one called the control channel, one called the traffic channel. Now the traffic channel is used to carry voice and some data. The control channels are used to set up they set up the call and for maintaining calls and so on. So they basically establish a relationship between the mobile unit and the nearest base. So when you switch on the mobile, for instance, the control channel that is on, and it is through the control channel that your device will be talking to the base station that is there in that area. Okay, so that's what we have. Okay. Right, so this is the basic structure. So now let's look at how we make calls and handle mobility when we in this kind of a simple 2G network. So if you look at the network, we normally use certain terms, right? We talk about something called a home network. Now, home network is the network of the cellular provider you subscribe to. For example, you may be subscribed to Airtel or BSNL. So that is your home network. So at the home network, right, there will be something called a home location register, HLR. Now, this HLR is it's like a huge database which has all information about your calls, right? So network and permanent cell phone number, the profile information, what kind of services you have, what are your preferences, your billing details, information about your current location. You may be in some other network, right? But where are you currently? That information will all be stored in your home location register. So then we talk about something called a visited network, that is the network in which the mobile currently resides. So let's say you belong to a particular, let's say I belong to Chennai. I'm moving to, let's say I'm just traveling to Delhi. So in which case, when I contact the Delhi network, right, that becomes my visited network. Chennai will always remain my home network. So at the home network, there will also be something called a visitor location register, right? I mean, at every network, there will be something called a visitor location register, which keeps track of who are the users who are currently in that particular network. So when I am roaming in Delhi, for instance, so my information will be there in the VLR at Delhi. Okay. Now, even if I am roaming in, I mean, even if I am not roaming, even if I am in my own home network, that information also will be at the VLR in my home network. Right? So the VLR has complete details about all the people who are there in that particular area, who belong to that same area plus those who are visiting. Okay, that's the idea. So now let's look at how the routing basically will get done. So let's say we have a caller here calling from some other network, okay, and he is calling through the public switch network, okay, through the to a particular user. The user, let's say, is here. Now the user actually belongs to this this network. This is home network, but now he is visiting some other network. So let's look at what happens. First, the call will be based on his number, will be routed only to his home mobile switching center. But the home mobile switching center will have information that this person is actually roaming in a different area. So what this will do is, it will now consult the HLR, get the roaming number of the mobile in the visited network, right, and transfer the call to that mobile switching center, right. So now what this switching center will do is, it knows where this person is currently located, right, through that particular base station to which he is connected. It will route the call to that particular person. Okay. So, this is basically how the call will get completed. Okay. So, let us look at how the handoff will take. This is a very simple example to understand how the routing will be done. Now, let us say he is moving from one network to another. Now, one other thing that needs to be done is the handoff. That is, how do you hand off the call from one base station to another or from one MSC to another MSC. So, let us look at how that is done. So, handoff for instance is very simple. If you are within the same mobile switching center, control of the same mobile switching center, it is very simple. All you need to do is when you move from one base station to another base station, the old base station will realize that its strength, its signal strength is reducing, right. So, it will be able to immediately, so the device now it can talk to the device, right, and it can initiate a handoff to another mobile, to another BSS to which this particular user is currently moving, right. So, then the mobile switching center, since that is the one which is controlling both these base stations, it will make this transfer possible by routing all the calls from here to here. So, that is a very simple, it is a common MSC, we have absolutely no problem in handling this. Okay. So, let us see what happens when you have this complete set, the various steps that we have here. Okay. So, the first step that we have here will be that the old BSS informs the MSC of a handoff that is about to take place, okay, and it provides a list of new BSS to which this can be transferred. So, now the MSC what it does is it sets up the path to the new BSS. So, that is your step 2. Step 3, this new BSS now will allocate a mobile channel for use by this mobile, and now it will signal the old BSS, right, that it is now ready to make the call. So, it signals the MSC and the old BSS that it is ready to make the call. Now, the old BSS now tells the mobile that okay, handoff done, so you can now start talking to the new BSS. So, now the mobile will start talking to the new BSS, activate the new channel, and it will also signal to the MSC via this new BSS, right, that the handoff is complete. So, from now onwards it starts and the old BSS also, now the MSC will indicate that resources can be released. So, that will be released, and now the mobile now is connected to the new BSS. So, this is what happens. So, when you have different MSCs, so for instance he is moving from one MSC to another MSC to another MSC. So, what happens here is first the call will be routed to the first MSC, which is called as the anchor MSC, right. Now, when new MSCs add on, you kind of add it on to this chain. So, it will go from here to here, and from here it will be sent to this one. Okay. You can also do certain optimizations wherein for instance you can optimize the path by skipping this MSC and going from the anchor MSC to the final MSC, to the MSC that you are currently now connected to. Okay. So, these are things that are done to in order to facilitate mobility. Okay. So, these are basically the things that are handled in the 2G network. Okay. So, this is the evolution from 2G to 3G. So, we will be looking at how 2G to 3G evolution happens in a subsequent talk. Okay. So, to summarize, we have looked at the overview of cellular technology, the basics of 2G, the 2G architecture, and how calls are handled and when mobility is there in a 2G network. Okay. Thank you.